Every year, teams from all over the world come to Battle Mountain, Nevada to race human-powered vehicles. This is a sport that combines engineering and athleticism to find just how fast a human can go under their own power. Monash Human Power is a student team that creates human-powered vehicles to push the limits of engineering efficiency and innovation. This year, we raced our version 3 bike at Battle Mountain in the US, which has been crowned the fastest bike in Australia. Some previous limiting factors have been aerodynamic design, where some challenges have been in not capitalizing on extensive laminar boundary layers and pressure recovery. This project aims not only to assist MHP's next bike design to be competitive with current world-class teams, but also revolutionize the way in which we design future models. This project has laid the groundwork for rapid prototyping and testing of fairing models for future members of the team by establishing industry-based systems engineering standards and utilizing high-performance design and analysis techniques. We hope to be competitive on the world stage when we return.
Our systems engineering approach was derived from OOSEM, or Object Oriented Systems Engineering Method, initially developed by Lockheed Martin. It focuses on enforcing stakeholder needs and requirements by a central model, which helped reduce upfront documentation and better understand the interactions between complex requirements. While not all of our goals were achieved, the development and application of this comprehensive plan has already been applied to the wider team in a more generalized model. The first step in our systems engineering approach was determining the stakeholders of this project. This included MHP management, the riders, everybody involved in the manufacturing, as well as the university itself. From interviews and workshops, a comprehensive set of needs were established and evaluated. These were then translated into technical requirements through requirements engineering. These were combined and reviewed for conflicts or other considerations and compiled into two databases. Both of these databases were reviewed and updated throughout the year based on periodic reviews with stakeholders. Our requirements were directly enforced into the CAD model of both the package space and fairing designs. For example, one requirement was a clearance of 10 millimeters to allow for extra material when manufacturing around the skid zone, which is the zone which sustains the most abrasion damage in the event of a crash. Therefore, a plane was created at a 10 millimeter offset away from the rider geometry and included in the package space. From this methodology, the high-level aims of our project were that our design must be safe for riders and bystanders at all time, have a competitive top speed, have adequate space for future systems, be easy to operate in the expected conditions, and be marketable. A package space was required to capture the space needed for the rider, their natural movement, some indication of the wheels and future chassis, and any other safety features that we needed. It was decided early on in the project that this bike should be designed to fit all of our current riders, and because of this, the dimensions of our largest rider were taken and translated into the model of a mannequin. It was assumed that all smaller riders would be accommodated for by variability of the internal chassis, for example, a moving seat. Then, with consultation from the chassis and rider teams, an approximation of the important features of a future chassis were created and combined with the mannequin. This allowed us to create a model that moved in a realistic way while riding. Using a previous MHP project aimed at determining the optimum riding position for comfort and performance, the rider's approximate positioning was also applied. And with all of this, a dynamic package space was created and verified that accurately traced out the movement of a rider in our chosen position. Finally, we added features like the roll hoop, materials, and movement tolerances, helmets, and more to most accurately reflect a real rider in action.
Using CAD, we could then construct fairing shapes around this package space. First off, a sound understanding of aerodynamic theory and competition is crucial. Through the research phase, techniques for developing fairing shapes more simply than before were found to be very effective. These promised greater surface continuity and curvature control. Notably, some obvious similarities in lengthwise pressure profile were found for several high-performing competitor designs. From here, the basic requirements for achieving extended lateral laminar flow were studied by tailoring front fairing geometry to maintain a controlled and consistent favorable pressure gradient. Initial fairing concepts were used to experiment with various forms and pressure profiles. Iterative simulation guided our modifications to the models to more closely match these desired pressure profiles. Those delivering the greatest drag reduction were carried over and refined further. The final model was influenced by these smaller versions, but scaled to fully accommodate the multi-rider package space and all the other requirements outlined in the systems engineering framework. CAD modeling techniques began with simple lofts defined over key package space regions. Testing with new surface techniques used by other teams around the nose points and rear wheel skirts yielded some improvements both for CFD and for our modeling simplicity. Along with greater general understanding of fairing performance, this allowed for some later simulations to achieve laminar extension to around 60 to 70% of their length.
Using ANSYS Fluent, we can more readily test different concepts than manufacturing model for the wind tunnel. The physics model that we used was transition SST. Due to the nature of the bike, we don't really see separation. However, we do see transition, and this affects our seamline placement and drag values. Some modeling was done using K-omega SST, another physics model, but there was consistently a difference in drag output of around 1 Newton higher than in transition SST sims. The final model simulation have been yielding CDA values of around 0.0127 with package space incorporated. This gives a fantastic 16 km/h increase over V3. Of course, these simulations need to be validated in the wind tunnel. However, we can be confident that these results are fairly accurate from the wind tunnel testing explained later. Many assessments of the CFD show that simulations involving the wheels drastically affect CDA calculations. The final model was increasing to outside the target zone of 0.018.
A promising model was 3D printed using the Prusa i3s. 3D printing allows for rapid manufacturing of designs. However, the printing bed was very small, which meant that the model had to be broken down into 22 separate pieces, which led to the presence of many seam lines. This meant that the likelihood of failed prints increased and the effects of warping added up to have a large impact. The models were then coated in fiberglass and epoxy and sanded to create a smooth surface. While the surface finish was improved over the 3D printing surface, it wasn't able to be perfectly smooth and even everywhere around the fairing. The mounts were then cut from steel plates and welded together.
The model was created and tested in the 2x2 meter wind tunnel at Monash University. Through getting force measurements and wake profiles, we were able to measure the performance of the model and the accuracy of our CFD. On initial inspection, it can be seen that the model is able to give better results than the previous two bikes. A limitation of the small wind tunnel is that it isn't able to get to the same speeds as the wind tunnel which the previous bikes were tested in. You can see that our model at a certain point increases in drag, while you'd expect CDA to decrease with increasing velocity or Reynolds number. This is due to a manufacturing defect in the tail, which is creating a vortex in the wake of the bike. These results do look promising, and with better manufacturing, we should expect to see better performance. Comparing the wake from the wind tunnel to CFD, we see that our simulations are similar to the actual wake profile. Additionally, the vortex and support interference is greater in the wind tunnel than it is in CFD.
When it comes to future testing, other methods we're considering for manufacturing models. But due to budgetary and time constraints, these methods were not completed, but the plan for future implementation was created. One option was to use CNC, which would be very accurate, but it comes with a greater attached cost and more required expertise. Negative molding can also be an option where the parts would be made using resin infusion onto a pre-layered fiberglass. This method, though, would still require a large amount of 3D printing.
While there have been some difficulties in this project, it has served as a valuable platform for validating our rapid prototyping methodology. The analysis of pressure recovery theory and extended laminar body demonstrates promising and actionable outcomes to future work. Moreover, the observed alignment between CFD and practical results is a noteworthy validation of our computational simulations. This process is one of continuous improvement in iterative design and manufacturing, and each successive speed bike that MHP deem necessary to build can do so on the solid foundation that this FYP is given. Thank you.